So we will talk about hypothesis tests. Again, we're dealing with one sample. Numeric variable. It's a hypothesis test about the mean of a population. Okay? So, for a hypothesis test, one sample numeric variable, your null hypothesis will be that the population mean mu is equal to some number. And I'm just going to make up a number here, not necessarily this for all problems, but your null hypothesis is that the mean of the population is some number like 8. The alternative is that mu is not 8, or is greater than 8, or is less than 8, okay? Okay, depending on how the question is written. On the situation. Okay. Your test statistic which is a t-score is going to be equal to x bar minus the mu from the null hypothesis divided by the standard error. And the standard error is s over the square root of n. The next thing we do in the process is look up the test statistic in the t-table to get the tail area, which we learned how to do already. Once you have your tail area, you leave it as is for your p-value, or you double it to get your p-value. When do we leave it as is and say my tail area is the p-value? When it's one tail. And we double it when it's two tail. And when is it two tail? When there's a not equal sign. Okay? So either leave or double tail area to get your p-value. So far so good?
Yes. Yes.
And then your p-value, what do you do with that? You compare it to alpha or 5% or whatever it is, and you decide whether to reject the null hypothesis or not reject the null hypothesis. Okay, so based on your p-value, either reject H0 or do not reject. So that seems pretty reasonable, right? Not too crazy? Okay. So your problem is, these are the bits of information you need to gather. So from your data, you will need to find n, x bar, and s. And from the problem, you must figure out the hypotheses. Alright, so I will put a problem up on the board, and I'll let you guys try to figure it out. I think you can do it, and if not, we will go over it together as a class anyway. Okay. Okay, so a man claims that the average chinchilla weighs. How much does the average chinchilla weigh?
8 pounds.
4 pounds?
What? 15 pounds? Okay, that's
8 pounds.
Not that big.
weight of a chinchilla.
It's like a
46.
It's like a rabbit.
All right. So man claims that it is between
250 grams.
okay, 1.8 kilograms. Throwing you off. Okay, so that's like
2 or 3 times.
okay. Actually, let's not do 1.8. Let's say 1.6 kilos. Okay, so a man claims that the average chinchilla weighs 1.6 kilograms. Okay, you are not quite so sure. All right, so we take a random sample. Somehow we get a random sample of chinchillas. Okay. Let's say 12 chinchillas. And the average weight of your sample is 1.3 kilograms with a standard deviation of 0.3 kilograms. Does this provide evidence that the population average is less than what the man claims? All right. How does that sound?
So it wouldn't be like it wouldn't be the population or the sample population average is less than
Okay,
what the
so
mentioned?
there's no such thing as a sample population because the sample comes from the population. So,
Oh, okay.
so we're asking about, we know that the sample average is 1.3. Okay, so it's not a question. Is the sample average different from what the man claims? Yes, my sample had an average of 1.3. There's no question about that. The question is, does my sample provide evidence about the population being different? So the population, we don't know the average of the population. When my sample is 1.3, is that evidence that the population is different from 1.6? Okay. there's no confidence interval for this. We are doing a hypothesis test. Okay? So I've kind of laid out what you need to do up here. Just remember that from the problem, you got to identify your data and figure out your hypotheses. So the first thing you should do is figure out your hypotheses and see if you can figure out everything else. I'll give you guys a few minutes to do that. I'll walk around. If we are completely befuddled,
It's asking what the population average was from.
So our average weight is less than the high school.
It's just, this is from like a population average. It's less than like.
So it should look like this.
It's,
Right?
no, it's bigger than 1.6.
But
Wait, why is it? Because we're looking at the moon. Remember how it's after 8:02? Oh, the moving average. Wow.
yeah, it's 18 is 1.3, right?
Yeah.
Then the one that you're saying is 1.6, so this is more. So it would be.
So the thing is this, the fact that we got 1.3 provide evidence that the population average is less than what the mass rate is. So it's less than, the population average is less than.
So you're just calculating, we're not like putting
Yeah.
population.
That's actually, like that.
So it's like this, right?
Yeah.
But actually like this, so
Yeah.
Why not? X bar is the sample mean. I just picked up on this 20 minutes ago.
X bar is not 1.6.
it's 1.3.
1.3?
X bar is 1.3. It is not polite to bloat a picture.
I was wrong.
Yeah. For what? Or no, 'cause you don't and then that's what you would put in the denominator.
Alright.
We're trying to see if the population average is less than 1.6.
That one should go.
Okay, how are we doing? Alright, well let's start off with identifying our data. N is 12. X bar is 1.3. S 0.3. Good. Okay. Our hypotheses. Hypothesis would be mu equals what? Mu equals 1.6. Alternative hypothesis? Mu is less than 1.6. So far, so good? Yes? No?
Yes.
Okay. All right. Some of you are yes, some of you are no. The no's. If you are so brave enough, can you ask me a question? Yes.
So is it less because our mean is 1.3? The average of our sample size is 1.3?
The question writes, does this provide evidence that the population average is less than what the man claims? Okay? Alright? So, based on that, we are saying the man claims 1.6, and we want to know, is it evidence that the population average mu is less than that? Okay? Yes.
Generally, our null hypothesis, is that going to be the first thing that, our null hypothesis, is that going to be the first thing that's stated in a question like this?
Not necessarily, okay? Not necessarily. The null hypothesis will always have an equal sign though, okay? Alright, so this part's good? Okay, let's figure out our test statistic, okay? So we first got to figure out our standard error. What is our standard error? It's going to be s over the square root of n. So that is 0.3 divided by the square root of 12 and
0.0.
okay. I believe all of you, but I cannot understand everybody when they say everything. Okay, so I get 0.0866.
So you don't round it?
I like to keep at least 4 decimals. Okay, I like to keep 4 decimals for steps within the problem. Okay, steps within the problem, keep 4 decimals. At the end of the problem, round down. Okay, so now we figure out our test statistic. So t is going to be 1.3 minus 1.6 divided by 0.0866. So I get negative 3.464 or something like that. Okay. Now what do we do? Okay. So now we look up your test statistic in the t-table and get the tail area. Okay. So to look it up in the t-table, I've got to find my degrees of freedom. What is my degrees of freedom?
11. 24.
N minus 1. So
11.
degrees of freedom is 11 degrees of freedom. So I'm looking up 11 degrees of freedom and a test statistic of negative 3.464.
That's the number we get
Okay,
that
yeah, the tail area.
Tail area?
So where is it in between?
So it's in between
106 and 406.
Yeah.
So my tail area for 11 degrees of freedom is going to be between
3.001.
okay, so T is between
Oh, 0.005 and 0.001.
okay, so it's going to be less than 0.005 but more than 0.001. And you might have written it the other way, and I will do it just to be nice here. But you're only going to see it written one way on the test or somewhere else, okay? Is this okay? Good. Alright, do I leave it as that, or do I double it to get my p-value?
Double to get p-value.
Leave
Just
it,
kidding,
leave it as is.
Both.
Leave it, you cannot do both, okay. We leave it as is because why? I have a less than sign here, meaning it's a one-tail test. One-tail test, so I leave my tail area as my p-value. So, my p-value, I don't know exactly what it is, but it's less than 0.005 and more than 0.001. Yes?
Professor, so if it was two-tailed, would you double the negative 3.464?
I would not double the negative 3.464. I would first find my tail area and then double my tail area.
So if it was
So-
two-tailed, you would double 0.005 and 0.0, okay.
So you do everything.
If we had a two-tailed test. When do we have a two-tailed test? When the alternative has a not equal sign.
Yeah, 0.001 times two.
Alright, one person at a time, so Lazine.
Alright, so that's the same thing with two tails, you would double what? So you would write both answers.
Yeah.
If
No, you would write.
If the alternative hypothesis had a not equal sign, then it's a two-tailed test. If it's a two-tailed test, I double my tail area, which means I multiply 0.001 by 2, and I multiply 0.005 by 2. Okay?
That's also when you reject the null hypothesis, right?
No, the rejecting of the null hypothesis is done by comparing our p-value to our alpha. Okay? Alright, so we figured out our tail area. We had a one-tailed test, so we leave our tail area as our p-value. Now that we have a p-value, what do? I compare my p-value to alpha or significance level. Now it was not specified in this problem, so that means we assume alpha is
0.05.
okay, so alpha is 0.05. So is our p-value bigger or smaller than alpha? Smaller, okay? So my p-value is smaller than alpha, and what does that mean?
HO is.
We reject
No.
the null hypothesis. And so what is the conclusion that we make? We say we have evidence Everyone's okay that we're rejecting the null?
No.
No, we're not okay. Okay. What part are we not okay about?
That
So my p-value is between 0.001 and 0.005. Is that less than alpha?
Yes.
Alpha is 5%.
How'd you put that alpha sign?
So if alpha, sometimes in the problem it will say use a significance level of this, or use alpha equal to this. Sometimes it's not written in the problem. If it's not written in the problem, assume alpha is 0.05.
Always? Always.
Always. Okay? If it's written in the problem, use what's written in the problem. If it's not written in the problem, assume 5%. Yes?
What are the homeworks that you did? You used 1%.
It was probably written in the problem that it was 1%. It was not? Okay. I will verify. Alright? Not that I don't believe you, but I feel like it should have been written in the problem if I did 1%. Yes.
You make sure that the YouTube guide was working, right? Because the last class it wasn't had problems.
Okay, I'm sorry about that. I just record the videos and I upload them, and I don't really check. It's so painful to hear yourself talking, so I try to avoid it if I can. Okay? No, I mean,
Is that why you started to type that?
no, I just got a little lazy there. Okay. But like, you know, you record your voice and then you listen to it later and you're like, oh gosh, this is terrible. So anyway, that's how I feel every time I have to watch one of my videos. All right.
Okay, so we reject the angel.
We reject the null, okay? Is that okay with everyone?
Yeah.
Now that we've rejected the null, that means we have evidence that what? we have evidence that this is false and that this is true. So we want to say we have evidence that this is true. So how do we write that in words?
We have evidence that the man's claim
The population average is less than what the man claims.
Alright, we have evidence that
It's more likely.
the average chinchilla what? Weighs less than 1.6 kilograms. And that is it.
Is that like our final answer? So our answer will like have that like explanation, and then we have to box the tail area thing.
You don't have to box that, but your final answer is we reject the null hypothesis. We have evidence that the average chinchilla weighs less than 1.6 kilograms. Alright, be quiet please. I've gone through the process. I found my p-value. My p-value is less than alpha, so I reject the null. When I reject the null, it means we have evidence that the average chinchilla weighs less than 1.6 kilograms. If I go through the steps and I didn't reject the p-value, let's say I didn't reject the null, so my p-value ends up, let's say, being 10%. If my p-value is 10% and I do not reject the null, then it means, what is the last conclusion I said?
That it wasn't by chance. And then,
Okay, sorry.
am I wrong?
I don't know.
Do we just
I,
change it
you
to
have
this
to
song?
finish your sentence, but it didn't go the way I wanted it to go.
Oh,
So I'm
okay,
gonna just
sorry.
stop you right there, okay? So, but thank you for volunteering. Okay, so if our p-value were greater than alpha, we would say we do not reject the null, and then I would say we do not have evidence that the average chinchilla is not. Okay, we do not have evidence that this is wrong, okay? We do not have evidence that the null hypothesis is wrong, so we do not have evidence that the average chinchilla weighs less than 1.6.
So we just put not in front of it.
Yes. Yeah, I just got confused for a second as I was talking.
You don't
so
have
sometimes that happens, okay? So we would write, we do not have evidence that the average chinchilla weighs less than 1.6 kilograms.
Now, do you give us a problem where it has the equals
Yeah, I could give you a problem, but maybe not
Yeah.
for a one sample thing. Okay, we have to cover the cases where we have two samples, so maybe I'll do one of those at that time. All right, I'm gonna move on here. Okay. This isn't so bad, right?
It's okay.
It's the best. Okay. All right, now we're going to deal with situations where we have two samples. Okay. So, same thing with proportions. Proportions, we had one sample when we made confidence intervals. We had one sample and we did hypothesis tests. And then we had two samples and we did a hypothesis test. We actually didn't do a confidence interval for two sample proportions. I hope no one's brokenhearted about that. Okay. But we do have two sample confidence intervals for means, and we have two sample hypothesis tests for means. Okay. So we're going to tackle each of those. Alright, so we're going to do confidence intervals. Okay. Two samples. Numeric variable, meaning we are dealing with means. So we have two samples. This means we're going to have 6 pieces of information for our data. Okay, so our data has sample 1, which will have N1, X bar 1, and S1. Okay, this just means the N, X bar, and S coming from sample 1. The other bits of data that you will need is basically the same thing from sample 2. N2, X bar 2, and S2. Again, once you figure out that you have 2 samples and you're dealing with numeric variables or means, it makes your life easier if you identify these pieces first, and then you go out and solve the problem. Okay. The standard error is going to be an ugly formula, nothing we can do about it, alright? Just like the other situation, okay? S1 squared over N1 plus S2 squared over N2. It's not the worst. It just looks bad. But it just looks a little bad, okay? And your confidence interval, x bar 1 minus x bar 2 goes in the center. This is the center of the interval. Plus or minus t star times the standard error, which is S1 squared over N1 plus S2 squared over N2. Okay. Now, picking t star requires degrees of freedom and your confidence level. So, the degrees of freedom is going to be n minus 1, but which n do you use? Use whichever n is smaller between n1 and n2, okay? You have 2 n's, use the smaller n. That's it.
That's it?
That's it. Alright, so let's try this out. Average weight of a guinea pig. That's great, thank you. Okay, so my phone did indeed just talk to me, so yeah, okay. Alright, so let's, we're going to make a confidence interval for the difference between the average weight of a chinchilla and the average weight of a guinea pig, okay? I don't know why I'm excited. It's okay.
I feel honestly.
let's make a 90. Make a 95% confidence interval. mu1 minus mu2. So figure out your data, then see if you can identify your T star and answer the problem. So just check, you can check your work along the way. You got this, you're in good shape. If you're not, maybe a mistake along the way.
Doesn't matter. I just wanted to see if you wanna do everything inside of it before you. Oh, square?
How are we doing?
I need a calculator.
You need a calculator?
No,
You need
help.
calculator help. Alright, well let's see what we've got, okay? N1 will be our chinchillas. Our sample 1 will be chinchillas, and sample 2 will be the guinea pigs. N1 is 12, X bar 1, 1.3, and S1, 0.3. N2, 10, X bar 2, 1.2, and S2, 0.25. Great. Alright, let's figure out our standard error. It's going to be 0.3 squared over 12 plus 0.25 squared over 10. Okay, so when you do this, you should get 0.1173. Some of you are asking, how do I do this on the calculator, okay? Assuming you've got at least a scientific calculator, the buttons you should push are 0.3, and then you probably have a square button, an x2 button, okay? Then you hit the divide key, and you enter 12, and then you hit plus, and then do 0.25, square button, divide key, 10, and then hit equals. You'll get some number there, and then hit square root button of the answer, and hit equals. We should get 0.11726.
Yeah.
My calculator was showing me like scientific notation.
Okay, so you've got to change it to floating point notation.
If I'm off on, I have instead 0.1174.
Fine, no problem. Are we good? Alright. So we have the standard error, okay. What is my T star? How many degrees of freedom am I going to use? I'm going to use 9 degrees of freedom because I'm doing n minus 1 and I'm using the smaller n. And I have 95% confidence, so my T star is 2.262. Okay? And so now I'm plugging in all of these numbers. X bar 1, 1.3 minus X bar 2, 1.2, plus or minus 2.262 times, this whole thing came out to be 0.1173. So I have 0.2653, and I have 0.1 plus or minus 0.2653. So far, so good. Alright. I'd like to see thumbs up and smiles.
Never mind.
No? Are you sure?
I got thinking in my head first.
Okay. Some of you guys are still catching up on the writing. Alright, and then so when I do this, on the high end I get 0.3653, and on the low end, what do I get? Negative 0.1653. Okay, so let me just, for simplicity's sake, let's round this to positive 0.37 and negative 0.17. This is my confidence interval. Alright, is that okay? And this is in kilograms, because everything's being done in kilograms. So, my confidence interval. This is the confidence interval for what? The difference in weight. So we are asking, what is the difference in average weight of chinchillas and guinea pigs? So we are saying the average chinchilla is between 0.37 kilograms more and 0.17 kilograms less than the average guinea pig. Does that make sense? Yes. I will write it on the board, okay? But I'm saying I'm 95% confident that the average chinchilla is between basically 0.37 kilograms more and 0.17 kilograms less than the average guinea pig. Sarah?
So you want us to always round that?
No, I'm just rounding it so it's easier for me to talk, okay? Because it's cumbersome to say 0.3653. It's good to keep decimals, but I'm just rounding it for conversation. Yes.
Can you further elaborate how we got to, I get the mu1 minus mu2, but how do we just treat it like a regular confidence interval at that point?
Yes.
Okay.
So I do x bar 1 minus x bar 2, and I have 0.1, and it's 0.1 plus or minus that side, which is 0.2653.
Okay.
Nicole?
Could you re-say that sentence where you said the average chinchilla weighs more but less than the big?
Yes. It's a confusing sounding sentence, and there's a reason why. Okay? Let me change the conversation to, let's say, men and women. Okay? Because I think this will be easier for us to hear out. Okay. So if I said make a confidence interval for the difference in heights between men and women, at the end of the day, my confidence interval will probably be something like this. I am 95% confident that the average height of men is between 4 and 8 inches taller than the average height of women. And does that sound okay to you?
Yes.
I'm 95% confident that basically the average man is between 4 to 8 inches taller than the average woman. Does that mean every man is taller than every woman? No. Okay, but if we're looking at the average man, average woman, he's going to be between 4 to 8 inches taller than the average woman. Okay. However, let's say we were talking about IQ scores. Average male IQ, average female IQ. Okay? Now, based on the sample data I take, my confidence interval will probably be something like this. I'm 95% confident that the average male IQ is between 6 points higher and 6 points lower than the average female IQ. Okay? Does that sound okay? So, in the first one, if I said, do we have evidence that the average male is taller than the average female, you would say?
No.
You would say yes, because the average male is between 4 to 8 inches taller than the average female. In the second situation, where I said the average male IQ is between 6 points higher and 6 points lower than the average female IQ, and I asked, do we have evidence that the average male IQ is different from the average female IQ, you would say no, okay, because within that interval, it's very possible that the difference between average IQ is 0 points, which would mean they would have the same average IQ. But as for the height difference, we seem to have pretty clear evidence that the average male is taller than the average female. All right. So, here, talking about chinchillas and guinea pigs, I'm saying I am 95% confident that the average chinchilla is between 0.37 kilograms more and 0.17 kilograms less than the average guinea pig. So what does that mean? Do we have evidence that the average chinchilla is different from the average guinea pig?
Yeah.
No, we don't, because it's very well possible that 0 kilograms, that the difference between the average chinchilla and the average guinea pig is 0 kilograms. Does that prove that the average chinchilla and average guinea pig weigh the same? No, it's just, I looked at 12 chinchillas and 10 guinea pigs. That's not enough evidence for me to make a decision about the difference between chinchillas and guinea pigs. Sarah?
You're going to want us to write out that statement again?
I will write it out for you, okay? I was talking first so we kind of get an idea, and I'll write it up on the board. Yes.
How do we know that our confidence interval applies to chinchillas rather than guinea pigs?
because I said chinchillas is sample 1 and guinea pigs is sample 2. This was an arbitrary assignment. I could have just as easily called guinea pig sample 1 and chinchillas sample 2, and I will explain what would have happened if we did that. Okay.
In this problem, we assume that all the assumptions are met for confidence intervals? Or-
Yes, yes. I'll talk about the assumptions and conditions for confidence intervals and hypothesis tests at the very end of today's lecture. Okay, so I would write I am 95% confident that the average chinchilla weight is between 0.37 kilograms more and 0.17 kilograms less than the average guinea pig weight. So 0 kilograms is within my interval. Okay. This is an interval for the difference. So it's very possible that the difference is 0 kilograms. So I would say I do not have evidence that the average weight of chinchillas, and I'm just abbreviating it, chinchillas and guinea pigs are different. The average weights are different. Zero popped up from the fact that no difference means the difference is 0. If two things are the same, what's the difference between them? 0. Okay? So we're asking, do we have evidence that they could be the same, or do we have evidence that they're different? If we're looking for that, we're looking to see if 0 is a possible difference.
So 0 wasn't a possible difference, then our statement would be
Different. Okay. So I'll write all the other ones regarding the human height and stuff like that. Okay. Is this okay? All right. So this is an example where 0 is in the interval. You do not have evidence of a difference. Okay. Different problem. Let's say the conclusion. The interval is 4 inches to 8 inches. Okay? So we would say I am 95% confident that the average male height is between 4 and 8 inches taller than the average female height. Okay? And we would say we have evidence that males, that the average male is taller than the average female. Okay? Because 0 is not in the interval.
so if we didn't have the 0, then we would have evidence that the weights of chinchillas and
If
guinea
0 was
pigs-
not in the interval, that's correct.
Okay.
Okay? 0 is in the interval, you don't have evidence of a difference. 0 is in the interval. I'm sorry, if 0 is in the interval, you do not have evidence of a difference. If 0 is not in the interval, you do have evidence of a difference. Okay? What would have happened if I labeled chinchillas group 2 or sample 2 and guinea pigs sample 1? Over here, the only thing that would change is that I would be doing 1.2 minus 1.3. Okay? Standard error is the same. My t star is the same. The only thing here is that this changes from positive 0.1 to negative 0.1. And all that really does is change the signs of my confidence interval. Okay? Your conclusion will end up being the same. All that changes would be, here I'm saying chinchillas are between 0.37 kilograms more and 0.17 kilograms less. It would change my sentence technically, and it doesn't even matter if we say it this way or not. It would change it to the average guinea pig is between 0.37 kilograms less and 0.17 kilograms more than the average chinchilla. Okay. In the same way, if I switch the signs around for this, over here, instead of saying I'm 95% confident that the average male is between 4 to 8 inches taller than the average female, I would be saying I'm 95% confident that the average female is between 4 to 8 inches shorter than the average male. You're saying the exact same thing, it's just from a different perspective, right? You can say the difference is positive if you're going from one to the other, or you could say the difference is negative, but we're saying the same thing. Okay? Yes?
How is 0 kilograms within the interval?
Because my interval goes from negative 0.17 kilograms to positive 0.37. So on the number line, right, I got positive 0.37 over here and negative 0.17 over here. 0 is in between. The first time you're exposed to anything, it's always a little uncomfortable, okay? You expose yourself a little bit more to it, you will learn to love this, okay? It's just like your first beer, or the first time you had coffee. Huh? Or I don't know. It's not true you loved it the very first time you tasted it? I don't know. Okay.
Is this like an example that would be on our quiz or final?
You know, I don't remember what questions I put on the quiz, okay? I have it detailed out. These types of examples are good to study, okay? All the examples I do in class, I do because I think they are useful to learn, all right? So this is the last situation and scenario, and I've got to work a little bit quickly, but it shouldn't be too surprising, okay? And this is hypothesis tests for 2 samples, and we're dealing with means again, or numeric variables. Do you guys remember how to do hypothesis tests for 2 samples with proportions? Okay, you just did them in your homework lesson. Or maybe last night, okay? It's done very similarly, except we're dealing with means and standard deviations. Okay? So, the null hypothesis is not P1 minus P2, but rather mu1 is equal to mu2, or alternatively, it could be rewritten as mu1 minus mu2 equals 0. Okay? So just like we did for proportions, but now we have mu. Alternative, mu1 doesn't equal mu2, or mu1 is less than mu2, or mu1 is greater than mu2. Again, depending on how the problem is written. And these would all correspond to alternative hypothesis. Is that okay? Alright, again, your data, n1, x bar 1, s1, n2, x bar 2, and s2. Your test statistic. It's going to be t is equal to x bar 1 minus x bar 2. Technically there's a minus 0, but we can ignore that quite often. Divided by the standard error. And our standard error is what we had before. S1 squared over n1 plus s2 squared over n2. This is all okay, right? It's not too much of a shock. We're just replacing p's with x bars and p's with mu's, and or p hats with x bars, and the standard error is now this. So once we have our test statistic, what do? Look up the test statistic. Where?
T-table.
In the t-table. And what do we get? To get your tail area. And then your tail area either becomes the p-value, or what do? Tail area times 2 becomes the p-value. And what are the rules regarding that? It's whether it's a one-tail or two-tail test. Once we have our p-value, what do?
We compare it to alpha.
Yeah, compare p-value to alpha. To decide whether to reject or not to reject the null hypothesis. And just in case it's not clear, sometimes this quantity, x bar 1 minus x bar 2, is also called the observed difference. Observed difference between means. Average weight of brown bear. Okay. All right. Good to know. Okay. So we want to know. Okay. So we're going to do a hypothesis test for the difference in weight between brown bears and black bears. Okay. So we take a random sample of 9 brown bears. Okay. The average weight is 590 pounds with a standard deviation of average weight of black bear. Okay. And we take a random sample of 6 black bears. Okay. And the average weight this is not going to be an interesting comparison. Okay, but let's try. Okay, 280 pounds with a standard deviation of 37 pounds. Okay. Provide statistical evidence Okay. So with this, see if you can come up with your hypotheses. All right. So the question just says, does this provide statistical evidence that there is a difference? Okay. So I'm not specifying that one is larger or smaller. So we just want to know, do we have evidence of a statistical difference? And that is the data that you have. Yes. Anna.
If you're just looking for a difference, can't we just see if the numbers are different without having to do anything?
Yeah, you know, I didn't realize the difference would be this stark. Okay. I was hoping it would be like 590 versus 550 or something like that, but it's not the case. Okay, but let's just go through it and see what happens when we do the statistical analysis. Okay, you can kind of look at this and say, yeah, it looks like black bears are smaller than brown bears. Okay. Alright, I realize that many of you are still working, but in the interest of time, going to work through the answer here, okay? Alright, so first off, let's figure out our hypotheses, okay? So the null hypothesis will always be mu1 equals mu2, or equivalently mu1 minus mu2 equals 0, okay? So I'm just going to go with this formulation over here. So my null hypothesis will always be mu1 minus mu2 equals 0. And my alternative will be what? Mu1 minus mu2 is
Not equal 0.
not equal to 0. Okay, and we choose not equal to 0 because this says a difference. It doesn't say we have evidence that brown bears weigh more or black bears weigh less or something like that. Alright, let's identify the bits of data that we have. Okay, so let's call sample 1 the brown bears. And sample 2 will be the black bears. Okay. What is N1? X bar 1?
590.
590. And S1?
48.
48. N2?
6.
X bar 2?
37.
And great. Okay. My test statistic is going to be 590 minus 280, technically minus 0, divided by the standard error, which is 48 squared over 9 plus 37 squared divided by 6.
I mean 6, yeah. 22.
What's that?
22.
22. Let me just
22.003.
22.003.
Or 4.
3.
I'd say 4 actually.
22.00 what?
3.8.
22.004. Yeah, I guess 22 is fine. Okay. So 590 minus 280. 310 divided by 22. Okay, yeah. So 14.09. Is that what we got?
Yes.
Okay, so that is my test statistic. My test statistic is 14.09 standard errors away from the mean of 0. Okay, that's a lot. But let's go to our table. How many degrees of freedom do I have?
5.
5 degrees of freedom, right? N minus 1, I'm using the smaller n. So I go to 5 degrees of